We defined refraction when we started this unit as the bending of a wave, the change in direction of a wave. We talked yesterday about why light changes direction when it goes from one medium to the other. Does anybody remember that? Does anybody remember why light changes direction when it goes from one medium to another? Yeah? Yeah, it either slows down or it speeds up, right? The change in speed leads to a change in direction. I'm going to call direction theta there. If v goes up, theta goes up. If v goes down, theta goes down. Now, there's one more thing that changes as a result of the speed changing, speeding up or slowing down. What else is it that changes? Yep. Good. As v goes up, the wavelength will go up. As the speed goes down, the wavelength will go down. There's one property of the wave that won't change even when you do go from one medium to another. One property of the wave that always remains the same. What is it? Yeah. Once the wave has been made, the frequency of the wave will never change. The speed will, and the speed changing causes the wavelength to change and causes the direction to change, but the frequency still doesn't change. If you had 5 waves in 1 second, you still have 5 waves in 1 second. It might be going faster or slower. It might be wider or narrower. It might be going in a different direction, but you still have 5 waves in 1 second. We defined a term yesterday that kind of extended this definition of refraction. That term was the index of refraction. Sometimes you might hear it called the refractive index, or if you go to your eye doctor might just call it the index. You have high index lenses or lower index lenses. The index of refraction we loosely define, this is how we understand it, as a measure of how much light bends. In the medium. So if you have a high index of refraction, you get more bending, right? A low index of refraction is less bending. Okay, that means that high index of refraction causes a bigger change in speed, and a low index of refraction causes less change in speed. Anybody remember the symbol for the index of refraction? N. Anybody remember the units for the index of refraction? It is a trap, you're right, because it's meters per second over meters per second, which cancel, which gives us no units. Good. Does anybody remember the equation for index of refraction, given, of course, that it is not on your data sheet? What is it? C over V. Good. What does C stand for, Janae? Yeah, it's the speed of light in a vacuum, which is always 3 times 10 to the 8 meters per second. And V is always the speed of light in the medium. V will always be, less than or equal to 3 times 10 to the 8 meters per second. It can be equal, but it's never going to be greater than 3 times 10 to the 8 meters per second. That means that N will always be what? Greater than or equal to 1. The index of refraction of air, well, the index of refraction of vacuum is exactly 1. The index of refraction of air is like 1.00 something. The index of refraction of water is about 1.3. The index of refraction of glass is about 1.5. Diamond is about 2.4. So as we go from air to water to glass to diamond, each of those materials bend light progressively more because of the bigger index of refraction, which of course means that it causes a bigger change in speed when it goes from air to water to glass to diamond. Now, we also said yesterday that glass or plastic or whatever material has a different index of refraction for each different color. If I shine white light, which I'm ironically drawing as a black line, white light that consists of all the colors, red, orange, yellow, green, blue, indigo, and violet. White light goes into this prism that has a different index of refraction for each color. Then we're going to find that the light bends a different amount. Red light bends a different amount than blue light. Which one bends more? Yeah, blue light bends more. That means that there is a higher index of refraction One of these days I'll get this. There we go. There is a higher index of refraction for the glass for blue light than there is for red light. Blue light bends more. Red light bends less. High frequencies, they don't have a higher index of refraction because light doesn't have an index of refraction. But the material has a higher index of refraction for high frequencies. So glass has a bigger index of refraction for blue than it would for red. Now, do I memorize that? No. I find it easier, to be honest, to just see a picture in my head. We talked in Unit 2 about the car going down the hill, right? I visualize, I see the car going down the hill to replace a charged particle accelerating. Okay, when I see this, and I'm trying to remember which one bends more and which one bends less, high frequency, high wavelength, low wavelength, and so on, all I do is memorize or bring back to my mind that poster that's on the wall. If I can see that poster, and I can see that red light is on the top and blue or violet light is on the bottom, then I can figure out from there that low frequencies have a lower index of refraction, and high frequencies have a higher index of refraction. And red light, which is a higher wavelength, will bend less, and so on and so on and so on. I can figure out whatever I need to figure out by just picturing that poster in my head. We talked about that yesterday, but we didn't formalize it in notes. I'm going to get you to copy this down now. As you do, keep in mind a couple of things. One, a little bit of a typo here. Should say a material has a slightly, not a lightly, a slightly different index of refraction for each frequency. The other thing that I want to draw to your attention is the word polychromatic. What do you think that means? Poly means what? Multi. Chromatic means color. Multi-colors. It could be white light with all the colors of the rainbow, or it could just be blue and red. Polychromatic means more than one color. When we have more than one color, whether it's 2 or 7, it will split up because the material has a different index of refraction for each of those different colors. Now I want to provide you with an equation, another one. This one is on your data sheet. It's more complicated, but at least it's on your data sheet. This one is called Snell's law. It provides for us a relationship between the angle that a wave goes into a medium and the angle that it comes out at, and the speed and the wavelength. And then, of course, the index of refraction of both of the materials. Let me draw a little picture here. This line represents the boundary between medium 1 and medium 2. This dotted line represents what we call the normal line. In Physics 20, we said normal force is the force that acts perpendicular to the ground. In physics, normal means 90 degrees. It means perpendicular. So the normal line is perpendicular to the boundary. And that's important because we always measure the angle from the normal line, not from the boundary, but from the normal line. Let's say that this is our first ray that enters the new medium. Let's call this theta 1. This is the angle at which it struck the boundary at. Let's call this theta 2. This is the angle at which it came out into the new material. Theta 2 in this case you can see is less than theta 1. Theta went down. Agree? Theta decreased. Have a look at the equation up there for a second. If theta goes down, why do you think theta went down? If the angle decreased, it must have decreased because the speed which is it? If it's theta 1 over theta 2, V1 over V2, then they're related to each other directly. That means if theta goes down, then that must be a result of V going down. If theta went up, then V increased, right? What about lambda? If theta goes down and v goes down, then lambda must go down. If theta goes down, v goes down, and lambda goes down, then n must go up. There's an inverse relationship there, right? v1 over v2, lambda 1 over lambda 2, and 2 over n1. So without labeling the indices of refraction of these two different materials, we know that because theta went down, the index of refraction must have increased. We went from a small n to a big N in this diagram. Now, on the right-hand side, we've got a table. You don't need to memorize anything on this table. They provide for us the average index of refraction of different materials. Keep in mind that they vary slightly with each different color, but on average, these are the values. Air is the only one that's on our data sheet. It says 1.00 for the index of refraction. All the other ones, if you need them, they'll be given to you. Probably not in the form of a table. It's probably going to be like a page of information with the index of refraction for crown glass buried somewhere in that page of information. It'll be there. You just have to find it. You never have to remember any of those numbers. And finally, this equation has 4 parts to it. You never need to use all 4 parts. You only have to use 2 of the 4 parts. Which 2 do you use? Depends on what you're given, what you're looking for. Pick the 2 parts that seem to make the most sense when you look at your givens. Okay, I want to do 2 questions here. One question is pretty straightforward. The other question is a little bit tougher, but for the most part, I think you're going to find that they're both relatively straightforward here. Here's the first one. Calculate the speed of light in a ruby. On our table, we see that the index of refraction of ruby is 1.54. That's given to me. How do you think you're going to find V? What is it? Sorry? Okay, the speed of light in a vacuum is 3.00 times 10 to the 8. Right? Sure, we can write that down for all of these problems, right? Whether we use it or not, it's certainly there. Remember that one equation that's not on our data sheet? The one that we looked at yesterday, n is equal to c over v? Want to find v, let's just rearrange it and say it's c over n. c is 3 times 10 to the 8, and n is 1.54. Before we calculate that, would you expect v to be bigger or smaller than 3 times 10 to the 8? Good? Got to be smaller, right? You can't have a speed bigger than 3 times 10 to the 8. When we do this, it works out to be 1.95 times 10 to the 8 meters per second. That's a reasonable speed. When you solve for one of these questions, v will always be 10 to the 8. It's never going to be more or less than 10 to the 8. And it will always be a number, a base, that is less than 3. So somewhere between usually 1 and 3 times 10 to the 8 meters per second. Parker? Yeah, I got the 1.54 from the table. That's right. So you get a question like that on a test, look for the index of refraction, because you'll find it somewhere. It may not be as tidy as this, Parker, in a chart or a table. It may be, you might have 13 numbers given to you in a massive paragraph of information. One of those numbers would be that index of refraction. One more example that I want to do here. Example number 2 says light passes from water to ice. By that we mean liquid water to ice, right? At an angle of 40 degrees. There's my boundary. There's my normal line. Let's say that this is water. It's going from liquid water. Liquid water has an index of refraction, see at our table, 1.33. To ice, which has an index of refraction of 1.31 on our table. Again, you don't need to memorize those numbers. The ray of light is coming down and striking the boundary like this. It passes at an angle of 40 degrees. We want to know this angle right here that it struck it at, the angle of incidence, we call it. Is theta 1 going to be bigger or smaller than 40 degrees? n went down, theta will go up. Theta 1 over theta 2 equals n2 over n1. Remember that equation? So n went down, 1.33 to 1.31. Theta will go up. So we're going to find that theta 2, which is 40 degrees, is bigger than theta 1. Now we've got to solve for theta 1. Here's our equation. Sine theta 1 over sine theta 2 equals v1 over v2 equals lambda 1 over lambda 2 equals n2 over n1. Which two parts of that equation do you want to use? The n's and the sines. Right, so let's say sine theta 1 over sine 40 equals n2. Make sure you get these in the right order. n2 over n1. 1.31 over 1.33. Let's say 1.31 divided by 1.33. Okay, that's the right-hand side. Let's multiply that by sine 40. So I get sine theta 1 is 0.6331. And then how do you find theta 1? Inverse sine, yeah. Second function, sine 39.3 degrees. Is theta 1 smaller than theta 2? Did we expect it to be? Yeah, n went down. That means v went up, lambda went up, and theta went up. Not by much. It went up from 39 to 40 degrees, so it didn't go up by much, but it still went up. I'd like you to take a look at, for the weekend, worksheet number 17. There's a number of questions on this sheet. I only want you to work on questions 1 to 7. Questions 1 to 7 for Monday, please. Those should go relatively quickly, probably 15, 20 minutes. Note that 1 and 2 are a little bit simpler. You got to remember that equation that I taught you yesterday. The rest of the questions, 3 through 7, will use this new equation, Snell's law, sine theta 1 over sine theta 2, and so on. When you're using that Snell's law equation, sine theta 1 over sine theta 2, v1 over v2, make sure you draw the picture. Okay, draw the picture. That usually ends up making life easier for you. You want to write down your givens anyways. You might as well do it in the form of a picture.